When work is done against a conservative force, like gravitational force, it gets stored as potential energy. Let's consider a body lifted vertically to a height h from the surface of the Earth. Some work needs to be done against the gravitational force of the Earth to lift the body, which is stored as potential energy in the body. When the body is released from height h, the body gains kinetic energy and loses an equal amount of potential energy. The law of conservation of energy holds good in this case, as the total energy of the system is constant. Like gravitational force, the electrostatic force between two charges at rest, expressed by Coulomb's law, is also a conservative force. The gravitational force between masses m1 and m2, separated by a distance d, is expressed as g into m1 m2 by d square, where g is the universal gravitational constant, which is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. We can see that the gravitational force F is inversely proportional to the square of the distance d between the masses. Similarly, the Coulomb or the electrostatic force F between charges Q1 and Q2, separated by a distance d, is expressed as K into Q1 Q2 by d square, where K is a constant which is equal to 1 by 4 pi epsilon naught. We can say that the electrostatic force F is inversely proportional to the square of the distance d between the charges. When a force acting between two bodies is inversely proportional to the square of the distance between them, that force is said to be obeying the inverse square law. We observe that both gravitational force and electrostatic force obey the inverse square law. We know that work done against gravitational force is stored as gravitational potential energy for the mass in the gravitational field. Similarly, work done against electrostatic force is stored as electrostatic potential energy in a charged particle in an electric field.